In this recording, we'll try to describe what makes a capacitor work or operate the way it operates. Okay, to do that, I'm going to go first to the simulation that we had before. Okay, what I have here, I added a battery, and I'm going to put a voltmeter across the battery, so it's reading for me 9 volts, meaning that the electrical potential difference between this end of the battery and this end of the battery is 9 volts. What does that mean? It means that the charges in the battery, they have the charges that are already present there are going to have an additional energy if they move from this end to this end. This is very much like putting a mass on top of a table. When you put it on top of a table, it has more energy than if it were on the floor. So it's just waiting for an opportunity to let go of that energy. So what I'm going to do now, I'm going to take a wire, just a wire, and place it at both ends of the battery. Let's start just one end. And let's see what this is going to read. It reads again 9 volts. Remember, first, that the electrical potential throughout any conductor is going to be constant. And that's what we are seeing here. We are seeing a constant value when we move the probe on top of the conductor. So it is 9 volts throughout. So if I add another wire in the bottom, the story is not going to be any different. We should be able to read 9 volts, and that's what we are reading, 9 volts. Now I'm going to do something more interesting, like add a light bulb. Okay, the light bulb does not light up. We don't have a complete circuit, but the voltage here at the end of the light bulb is still 9 volts. Of course, the light bulb is made up of a wire. Okay, but if it were in power, if this electrical circuit was complete, we'll find a lower voltage here than the 9 volts. Okay, now what am I trying to get to from here? What I'm trying to get to is the charges are trying their best to move as far away from each other as they can. If the charges can move off the battery, they'll move off the battery. Actually, the story is a little bit more complicated than that, but as a visual way to think of what's happening, think where the battery, the positive end, I have a lot of positive charges that are trying to push each other, and negative end, negative charges trying to push each other away. Now when I add the conductors, even the device here like the light bulb, now what's going to happen? The charges are going to use this media, the device, the wires, to spread out in them to make sure that we have a zero electrical field inside the conductor and we have an equilibrium state. Okay, the story is not physically correct because actually charges in a battery are created only when you complete the circuit. But that's beyond the scope of this course. Now, what if I put another wire here? Let me remove this one here. What if I put another wire here and I approach it to this wire here? Okay, without touching it. So what's going to happen? This is connected to the positive lead. This one is connected to the positive lead. This one is connected to the negative lead. What do we know about charges? Positive and negatives attract. So this is what's happening here. This lead is connected to the positive lead, and this is connected to the negative lead. And what we are doing is, by having this flat piece of conductor next to this other flat piece of conductor, we are giving the charges more opportunities to interact with the charges from the other battery lead. We are giving them more opportunities to interact through that larger area. So for that reason, charges are going to accumulate here that are positive, and charges are going to accumulate here that are negative. Remember, actually, it is the negative charges that are going to move. What this means is negative charges are going to be repelled from here, going into the battery, and allowing for some chemical reaction to occur to have more and more negative charges, and that's what's going to give the full charge in the capacitor. Now, from the description I just gave, the proximity of the plates is going to play a role on how much charge I'm going to be able to pile up on these plates. The closer they are to each other, the more charges I'm going to pile up. However, there is a problem. If they are so close to each other, charges might be able to have enough energy to jump over the gap between them, and then we have a leakage and a charge dissipation, and the capacitor does not store charge for me anymore. So it has to be close enough, but not too close. And then also another factor that looks like it might affect how much charge I can accumulate here. As I mentioned earlier, by having this flat piece of metal next to the other flat piece of metal is the idea of increasing the area over which there is going to be interaction. So the bigger this area is, the more charges I'm going to be able to pile up on the capacitor. Okay, now if we take that, so how do we make a capacitor? Any pair of conductors separated by a small distance. Two metal plates. You can take two pieces of aluminum foil and put them next to each other. That's a capacitor. What you have noticed, I hope, the capacitor stores separate charges. Positive charges in one end and negative charges in the other end. The net charge in a capacitor, the overall charge, is going to be zero. The amount of positive charge here is going to be equal to the amount of negative charge there, such that the overall charge is zero. So we have positive in one end, negative in one end, with a net charge of zero. The electrical field between the plates of a capacitor is going to be uniform. Okay, in this case, remember the electrical field is going to point away from the positive charges towards the negative charges. Now, we define what we call capacitance. The capacitance of a capacitor to store charge. So the key is to store charge. So the amount of charge in a capacitor is given by the capacitance of the capacitor times the voltage across the capacitor. So the voltage difference between the plates of the capacitor. C times V is equal to the charge stored in either plate of the capacitor. In one plate it's going to be positive, in the other plate it's going to be negative. The amount of energy stored in a capacitor is given by 1/2 of Q times V. 1/2 of the charge in the capacitor plate times the voltage across the plates. Now the capacitance, as we mentioned earlier, It's going to depend on the separation of the plates. The further apart the plates, the less charge we are going to be able to store in the capacitor. So for that reason, the capacitance is going to be inversely proportional to the separation of the plates. Now, the cross-sectional area of the plates, or the area of the plates, the larger the area, the more charges we are going to be able to collect. So it's going to be proportional, the capacitance is going to be proportional to the area of the capacitor. Now, so capacitance is given by C. It's equal to epsilon 0 A over D. Epsilon 0 is a constant. It is given by this. It is 1 over 4 pi K. K is the constant that we use in Coulomb's law. This is the value for epsilon 0. That's when we have a capacitor with air between the plates. If we have an insulator between the plates instead, what's going to happen if I have an insulator? The positive charges from here are going to repel the positive charges from the surface of the plate, from the surface of the insulator. So I'm going to have something like this. I mean, minus plus. And this is going to reproduce again throughout the insulator. Such that effectively the end of the insulator close to the negative plate of the capacitor is going to be positively charged. The end of the insulator closest to the positive plate of the capacitor is going to be negatively charged. So the effect of that is we are going to have an amount of charge plus Q here, an equal amount of charge but negative in this side of the insulator, and we are going to have the opposite on the other side, a plus Q here and a minus Q on the plate. So effectively what that does, it reduces the distance separating the plates of the capacitor. It's kind of, instead of that huge distance separating them, we have just a little bit here and a little bit here. So putting an insulator, what we call a dielectric, is an insulator between the plates, results in a bigger capacitance because it effectively diminishes that D. And the capacitance then becomes kappa times C0, where C0 is the capacitance in air, or in general, the expression for capacitance becomes kappa epsilon 0 A over D. So that's the capacitance when we have an insulator in between. Now, just to see some examples of capacitors in action, a variable capacitor like that one. Actually, I went to the wrong one. Okay, let's go to, I think it's here. What happens, you have an array of metal plates. This is a list of them here. 1, 2, 3, 4, 5, 6. And then some other metal plates. 1, 2, 3, 4, 5, 6. Now these two metal plates are separated. One of them is going to be the positively charged plate, and the other is the negatively charged plate. What we do to make the capacitance of this capacitor change is vary the area that these plates overlap. Here, for example, not much of them overlap. Here, they are on top of each other. When the area is small, I have a small capacitance, 50 picofarad in this case. When the area is large, I have 10 times as much capacitance, or 500 picofarads. So what I'm doing there is changing the area of the capacitor, A, in the capacitance equation. Okay, we'll go back to that. We are changing this A here. So in one case, the plates are just like this, where this is the overlap, and in another case, they are on top of each other, where we have full overlap. When we have full overlap, we have a bigger area, so a bigger capacitance. Okay, now let's check the other simulation in that page. Okay, now here is the factors that affect the capacitance. For example, if I have 0.1 square meters, I have 44 picofarads, and I have air in between. So if I divide that area by 5, I should get 1/5 of the capacitance. And let's do the reverse. 44 divided by 5 is 8.8 something. Okay, the other thing I can do, I can change the distance. I have 0.02, so if I have the distance, it should double, 17.71. Now the other thing I can do is change the dielectric. Here we have air. For example, if we put mica, that's one type of capacitor. See there, I have 95.63 as opposed to 17.71 when we had just air. If we have a different type of material like bakelite, I have no idea what bakelite is, it's 85 picofarads and so on. Now, one example of a use of a capacitor with a variable capacitance is a microphone, a condenser, what we call a condenser microphone. In this particular case, the plates of the microphone, one of them is going to be a sturdy plate, and another one is going to be made up of what we call a diaphragm, something that's going to be able to vibrate and move based on the sound near the microphone. Excuse me. So as it vibrates, the distance and the area of the capacitor are going to change. And those changes are going to affect the capacitance of the capacitor, and in affecting the capacitance, they are going to affect the electricity in this particular circuit, and that's going to translate into an electrical signal, a change in electrical signal that can be transmitted, amplified, and so on. Now, another application of variable capacitors is through this simulation. You see, this is actually a variable capacitor like the other one we played with a second ago. Now, what we have here is a circuit very similar to circuits that you have on your transistor radios or TV receivers. What you have an antenna that's collecting radio waves in a lot of different frequencies. What happens is you want your radio to detect only one frequency, and in this case it is detecting this frequency. You see this wave moving through, it's 89.4 megahertz. So what you do, whenever you tune your radio Whenever you turn that knob, what you are doing effectively is change the capacitance of a variable capacitor. As you change the capacitance, look at the way the plates are moving. See, the frequency of the signal changes as well. So that way you receive another signal. One last thing to mention before we stop describing capacitors, probably one of the largest capacitors we deal with every day is the capacitor made up of the ground and the clouds. Whenever there are clouds overhead, we are inside a huge capacitor because of the charges at the bottom of the clouds that are usually negative, resulting in positive charges at the surface of the Earth.